So this lesson here is a quick but hopefully extensive review of all the core aspects from Math 10 involving functions and specifically linear functions. And understanding what it means something is a function and how to graph functions and specifically linear functions is a big part of Math 10. Roughly half of the course involves linear functions to some extent. And so this is a review of many of those key ideas that we're going to build on in this course, in which we'll be dealing with quadratic functions instead of linear functions. And so I have a table here, and because each value of x has only one value of y, which means again for all these x values, for example, when x is 2, y is 0, and only 0. If you look, there's only one number in each of these y spots. That means for whatever number I pick for x, there's only one number out for y. Anytime we have something like that, we call it a function. You put one number in, you get one number out. And that's that's most of what we deal with, especially at these sort of stages. You put one number into something, you get one number out. And so this is a function here. I put, when I put -4 in for the x, I get -6 out for the y. And so I said, let's give this function a name. Let's call it f. So f is the name of this function. I put in a 4, I get out a 2. I put in a 6, I get out a 4. I put in an x, I get out a y. And so I can express any function as a series of ordered pairs. And an ordered pair are coordinates. For example, one ordered pair would be -4, -6. That relates to what I have right there. Another ordered pair would be -2 and -4. Another one would be 0, -2, and so on. Keep in mind the convention is the first variable is always your input, the x. The second number is always the output, usually y. And again, these are called ordered pairs, what you see right here. I've listed out 3 different ordered pairs, and I could go on, I just don't feel like listing them all out. I can also describe this relationship. I can describe this function in words, the relationship between x and y. And so to describe the relationship between x and y, I need to kind of see what happens as I go from here to here. I put in a 0, I get out a -2. I put in a 2, I get out a 0. I got to look at the relationship this way, from x to y. If I look at it this way, and I just go, I'm going up by 2, okay, but that's not telling me the relationship from x to y. That's telling me what happens as I look from left to right. But again, if I want to describe the relationship from x to y in words, I need to find some sort of pattern, some sort of consistent formula about what happens as I go from here to here. And if I look down every time, hopefully you can see that every single time I put a number in for x, the y is 2 less. That's the relationship we want to see. From x to y is always 2 less than x. So I can write that in words, and I can literally say y is 2 less than x. That's the relationship, or that's the function described in words. Well, if I can describe it in words, I can probably describe it as an equation. Just show function f as an equation of y in terms of x, which really means what I have up here as a simple statement expressed as an equation. And so I can say y equals x minus 2. Or, if I want to use something called function notation, I can say instead of y, I can say f of x equals x minus 2. These two equations mean the same thing. Just this is what we call function notation right here. And essentially, I told you earlier that I named the function f. That's what it says right here. Let's call it f. And that's why I have an f right here. And this x inside the brackets, that just means that x is the independent variable, which means x is the number that goes in, and whatever number comes out is the output. And again, this equation tells us that whatever number you put in, the x, all you got to do is subtract 2 from it. All right, and again, everything I've stated is something that comes up in Math 10. I'm just doing it quickly, so I'm hoping these things sound familiar. Hoping you're not learning this from scratch the first time. Otherwise, I'm going through this way too quickly. Just like domain and range. Domain and range are, for example, domain. The domain of a function is a list or an interval of all the numbers that can go into a function or be put into an equation. So those are usually the x variables. because by convention, x is usually represents the variable that we put into something. And range is a list or interval of all the numbers that come out of a function. And usually we call that y. By convention, x is what goes in, y is what comes out. And again, if that seems strange, well, that's exactly what I wrote right here. Right? If you want to figure out y, you have to know x first. And this equation here tells you the rule about how to go from x to y. You pick a number for x, you find out what goes for y. And so domain is a description of what numbers can go into the x, or go into a function, and range is a description of what can come out. So for example, if I look at this equation we already had, f of x equals x minus 2. X is what goes in, f of x is what comes out. So the domain is a description of all the possible numbers I can put into here. All the possible numbers I can replace x with. Well, all I'm doing once I have a number for x is I'm subtracting 2 from it. You can subtract 2 from any number. There's no number you cannot subtract 2 from. You can subtract 2 from any number, which means x can be any number, which means the domain can be any real number, we say. Literally, any number that exists that's real can be x. That said, if you hate words, you can write it like this. And this means the same thing. This means x belongs to the real number, we say, real numbers. That just means the same thing as before. X can be just literally pick any number, anything. There's no restrictions. X can be anything. The range is a list of what comes, or a description of what comes out. So now a little bit harder to think about, but the range is about what comes out of here after I subtract 2 from a number. Well, if I can put any number into this, and all I'm doing is subtracting 2, then any possible number that exists can eventually come out. For example, if I pick a number, 1,000. The number 1,000 will come out of this equation if I put the number 1,002 into it. And if I pick another number, how about 1,000,000? The number 1,000,000, sorry, that's there. Now I got 1,000,000. The number 1,000,000 will come out of this equation if I put 1,000,002 into the equation. So the idea is there's no number that can't come out. Any number I can think of, any number that's real, any possible number can come out of this, as long as I put as long as I put something that's 2 more than it in, which means the range is also any real number. Or again, for those haters of words, y belongs to the real numbers. Same thing. And so remember again, range has to do with what comes out, usually the y. Domain is what goes in. And sometimes you can't put any number you want into an equation. In fact, we've seen that already in this course, with both dealing with square roots or rational expressions. Sometimes you can't put certain numbers into an expression because you might divide by 0, or you might be square rooting a negative number. So sometimes it's not as simple as any number you want can go in. But in this case, it is. All right. And so also what I hope sounds familiar is if we have a relationship here between x and y, or inputs and outputs, I can graph that relationship. So I can show this relationship of f of x if I just graph, I say y equals f of x, or y equals x minus 2. Where x, again, represents the number that goes in, y represents the number that comes out. And so how do I graph this? I could make a table of values. And I could pick x and y, and pick some numbers for x, pick some numbers for y, and plot some points. That's kind of a grade 9, 8 way of looking at it. But in grade 10, you learned about slope and y-intercept. And so I have a linear equation right here. And the key is remembering the constant value is our y-intercept. And so -2, I know, must be where my line crosses the y-axis. And the coefficient of x, which in this case is 1, is the slope. And a slope of 1, remember slope is rise over run. So in this case, I can think of the number 1 as 1 divided by 1. And we usually call slope m. So in this case, this line of y equals x minus 2 goes through -2 on the y-intercept, on the y-axis, which I've already stated. And a slope of 1 means from any point on the line, I can find another point if I go up 1, over 1. A rise of 1, 1 over. And so if I just go up 1 and over 1, I get another point here. So I know this line goes through there. I can do that a few more times. And I can visualize this line really nicely. Keep in mind, a line is not a series of dots. It's an infinite, or if you're thinking of a series of dots, there's no gaps in it. I don't have to go up by whole numbers. And so if I grab a ruler, should I be able to find a ruler? No, here's a ruler. I should really connect this as a solid line, because again, there's no reason that I have to be dealing with just whole numbers. And so what I just sketched in red is my graph of this relationship, y equals f of x, or y equals x minus 2. So now the same function I've been dealing with again and again, I have now expressed as a graph. I've found its domain and range. I've expressed it in function notation, in terms of x and y, in words, as ordered pairs, as a table. Everything here relates back to the same function. OK, so in general, any function can be shown in a whole bunch of different ways. And thinking about what I've already showed, any function can be shown as a table. That was the first thing I showed you, as ordered pairs, which again are usually expressed x comma y. And if you have ordered pairs or a table, that means you can probably graph it. We almost certainly can. And if there's a relationship that has some sort of pattern, you can express it as an equation. And any equation can also be expressed in function notation. And as well, you can also usually express it in words. These are all things we've seen. For this course, the most important three are these three. The connection between graphs, equations, and understanding what function notation is. It's another way of showing an equation. As well, notice the graph I made was a straight line. We call it a linear function. And any graph, any function that forms a straight line when graphed is called a linear function. And again, that was the foundation of Math 10. OK, so let's look at another linear function, just not the same one as before. So I'm calling it g of x. I've just gone up the alphabet. Last one was f, now I'm g. And this equation here, g is the name of the function, x is the input. And I can see from looking at the equation that, g is the name of it. OK, x is what goes in. And if I look here, this tells me what to do. Whatever number I have for x, I multiply by 1/2, and then I add 2. OK, so with that said, let's make a graph of this. And again, I could make a table of values, or I can just remember what I said before. There's my y-intercept, so I know this line goes through positive 2 on the y-axis. And here's my slope, 1/2. And a slope of 1/2, or I'll say m equals 1/2. That means from any point on the line, I go up 1 over 1. And so I already know one point. That point I drew in red. So I go, I said up 1 over 1. I meant to say up 1 over 2. Right, there's the rise, there's the run. So up 1 over 2 brings me to there. And now I can visualize this line. I can do that again, up 1 over 2, up 1 over 2. Or I can also go, going back to this starting point, or my y-intercept, I can also go down 1 backwards 2. I can do that as well. Notice it all forms a straight line. So I can see this line, and again, I have way more than enough points than I really need to draw my nice straight line. There's my equation of, again, I can call this g of x, or I can call this 1/2 x plus 2. One's the kind of expressed in the function notation, one's the actual equation. That said, I've also found it's my y-intercept right there. There's the x-intercept. The y-intercept I knew right away by looking at the equation. And so that was pretty quick. Again, assuming we remember these things about slope and y-intercept. What's the domain and range of this particular function? Same as what we saw earlier. They're both all real numbers. This graph, and now that I have a graph, I can just see it. Domain, I kind of think left to right. This goes forever to the left and the right. It doesn't stop. Same thing up and down. It goes up forever, goes down forever. It never stops. So the domain and range must both be all real numbers. So all real numbers for x, all real numbers for y. And I mentioned this x-intercept at -4. An x-intercept is also known as the zero of a function, where it crosses the x-intercept. Or we say it's where the output equals 0. Because notice at -4, if I were to write the coordinates of this point, the coordinates of that x-intercept are -4, 0. That's always the case. Anytime a line crosses the x-axis anywhere,
or any function crosses the x-axis anywhere, the y-coordinate will be 0, which is why we tend to call them zeros as well. Okay, what if we have a linear equation that's not in slope-intercept form, like this? Well, there's a few options, but one is to put it into slope-intercept form. If I just look at it like this, I can't tell the slope or the y-intercept right away because I haven't solved for y. But let's solve for y. Let's add 3y to both sides. So I have x plus 9 on one side and 3y on the other. Again, I just have to isolate y. I don't have to have y on the left or right side. Divide everything by 3. And so now I have x divided by 3 plus 3 equals y. There's my equation. Now my equation is in a form in which I can see everything I need. For example, I can see this plus 3. That's my constant. That's my y-intercept. I know my line will go through here. I know that. The slope is the coefficient of x, which is 1 over 3. So my slope is up 1 over 3. Rise 1, run 3. And so from that point that I've already drawn, I know I can find another point if I go up 1 and to the right 3, or down 1 and backwards 3. Either way, I already have enough to draw my line. And so again, I'll label this. This was the equation of x over 3 plus 3. Or I could write the original equation, x minus 3y plus 9 equals 0. That original equation wasn't wrong. It just wasn't helpful. Notice if you look at that original equation, it's pretty easy to think, oh, the y-intercept's at 9. But no, it's not. That's because the equation's just not in the form we wanted. We can't expect equations to always be in the exact form that we want. Okay, that said, I could have actually graphed this function without, I didn't have to put it in slope-intercept form. I didn't have to put it into this form right here, which is like we call y, you can also call y equals mx plus b form. But slope-intercept form is what it's called. I could have also done it a little bit differently, and that's what I want to mention right here. I can also graph this by finding the x and y intercepts directly. How can I do that? Well, for example, if I want to find the x-intercepts, remember what I said earlier, that's where your y equals 0. It's where it crosses this line here. And anywhere on that x-axis, the y-coordinate will be 0. So I can quickly find the x-intercepts if I make my y equal to 0. If I get negative x minus 2 times 0 plus 10 equals 0. And the nice thing is that 0 is a great number. That middle term of negative 2 times 0 is just 0. Really, I just have negative x plus 10 equals 0. So if I can solve for x now, I know my x-intercept. It's pretty easy to solve for x if I just add x to both sides. Because then I have 10 on one side, I have x on the other. There's my x-intercept. I know this line goes through 10 on the x-axis. So a little bit off my graph. 6, 7, 8, 9, about right there. And that was quite quick. And so I can also find my y-intercept in a similar way. If I want to find the y-intercept, I can just go back to my equation and make x equal to 0. Because if I look at my y-axis, I don't care where I look on that line, the x-coordinates anywhere along that vertical line are 0. So I can do the same idea by making x equal to 0. So I have negative 0 minus 2y plus 10 equals 0. And again, that first term I don't really need to pay attention to. All I really have left is negative 2y plus 10 equals 0. And if I can solve for y, which I can do quite nicely, if I add 2y to both sides, I get 10 equals 2y, divide both sides by 2. I can see my y-intercept, 5 equals y. So there's my y-intercept. Which means I know my line goes through 5 on the y-axis, right there. And that's all I need. If I want to draw a line, I just need 2 points. I can now see these 2 points, which means I can grab a ruler and I can draw this with a good degree of accuracy. Oop, that's a highlighter. Take 2. There we go. And so in general, and this is true for anything, not just lines, because keep in mind, everything we're doing here is just meant to set up this next unit. If you ever want to find the x-intercept of any function, like we did right here, we made y equal to 0. And if we want to find the y-intercept of any function, we made x equal to 0. Which sounds backwards until you look at the graph and you realize, again, y, for example, y-intercepts, it's where it crosses the y-axis, and anywhere along the y-axis has an x coordinate of 0. All right, so before my final problem, I have two strangely simple-looking equations here, because they only have one variable. I have just x minus 2 and just y plus 3. What do these look like? Well, these are either vertical or horizontal lines, especially if I add 2 to both sides right here. And I get x equals 2. This means I want to visualize the line where x equals 2. The x coordinate equals 2. So where does x equal 2? Well, right here. But also anywhere above it or anywhere below it. The x coordinate will equal 2 anywhere on that vertical line. And so the equation of x equals 2, or some variation of it, represents a vertical line where x equals 2. And so as you can probably now guess, this is going to represent a horizontal line. If I subtract 3 from both sides, it gets a little bit more obvious. So where does y equal negative 3? Well, y equals negative 3 right here. But that's just one point. The y coordinate is negative 3 anywhere to the left or to the right of that point, which traces out a horizontal line. So again, the equation of y equals any number will represent a horizontal line at that number. And that leads me to the last question. Let's say you have an equation like this. F of x equals some number, a, times x, all minus 5. So my question is, if the value of a changes from 10 to 0, or just changes in general, what will change here? Like, if I were to think about the graph of this, and I had, f of x equals 1x minus 5, or 2x minus 5, or 3x minus 5. What will all these graphs have in common, and what will they have different? And again, I can also, what about 3.1x minus 5 and 3.2x minus 5? Again, what changes will that make? But also, what things will not change if I just change a? Well, hopefully we can realize that in all of these, they have the same constant of negative 5. So they'll always have the same y-intercept. Each time will be a line with a constant y-intercept, which means no matter what a is, it'll always go through negative 5 on the y-axis. The a is my slope. And so the larger a gets, the steeper the slope will get. For example, if the slope is 3, you can think of that as 3 over 1, so up 3 over 1. Up 3 over 1. And when we have 4x, the slope's going to be steeper. It's going to be up 4 over 1, and so on. So I can now visualize, without having to make a table of value, without actually having to graph anything, I can visualize as a changes, as a gets larger, I'm going to get a line that has a constant y-intercept at negative 5, but gets steeper and steeper and steeper. That's it. If you want a better visual, I'll go to Desmos here. And what I have here is right now the graph of ax minus 5, but right now a is 1. So what you're seeing here is a line with a y-intercept of negative 5 and a slope of 1. And notice you can see if I pick any point on this curve, on this line, I can find another point by going up 1 to the right 1, up 1 to the right 1. That's what a slope of 1 looks like. Now as I make a larger, notice the y-intercept stays put, but the slope keeps getting steeper and steeper and steeper. And you get the idea. The more I get to 10, the steeper it gets. And the closer I get to 1, or actually the closer I get to 0, the more horizontal it gets. If I get right to 0, I have a horizontal line. The slope is 0. And if I let it go into the negatives, now the slope is going down. I have a negative slope. For example, this here. This is a slope of negative 1. From any point, I can find another point by going down 1 over 1. Or if I go to negative 2, there we go. I can pick any point in the line. You can find another point by going down 2 over 1. So negative slope, 0 slope, positive slope, but they all have, if I let it just change, there, now it's going to kind of go back and forth. So even though the slope is constantly changing of this linear function, what's remaining constant, what's not changing, is the y-intercept, which makes complete sense, because if you look at the equation, that minus 5 has nothing to do with the a. The a is the coefficient of x, so the slope is constantly changing, but the y-intercept is not. So what I just reviewed here in these last, I don't know, 20-ish minutes, whatever it was, is a lot of Math 10, a lot of different parts. By no means have I covered everything from linear functions in Math 10, but this was a lot. So the idea, again, is not that you're learning this from scratch, is that I'm refreshing your memory of things you've learned about before. Going forwards, though, we're going to apply a lot of these same ideas, but not looking at lines, but looking at parabolas, which relate to quadratic functions. And that is the focus of a big chunk of this course. But it's time for me to stop now.